So the idea now is to talk about why for orthogonal matrix this holds. I mean, orthogonal matrix, we are talking about the real space. In the complex space, we are talking about a unitary matrix, but let's focus on the real space. So the proof will be very, very simple. You can take it to the complex space afterward. So what I want to talk about is why for orthogonal matrix it happens that if I take the transpose of an orthogonal matrix, I get the inverse of the matrix. I mean, A transpose equals A inverse for A orthogonal matrix. So why it happens? It comes from the property that for orthogonal matrix, A transpose equals I. But by definition, when you take two matrices, A and B, and it equals I, it means that B is the inverse of A by definition, because the inverse means that if I multiply a matrix by its inverse, I will get the identity matrix I. So from the fact that it happens for orthogonal matrix, we get that the A transpose is the inverse. But now we get to ask again why it happens, why A transpose equals I. And if we understand it, we can understand why A transpose equals the inverse, because this is the definition for inverse. So this is exactly the question. The answer is based on understanding what is orthogonal matrix. Orthogonal matrix is a matrix for which two vectors equals 1 if they are the same vector, and equals 0 because they are orthogonal for each other if they are not the same vector. You remember that in orthogonality, if vectors are orthogonal for each other, it means that the inner product between two different orthogonal vectors equals 0. And if the orthogonal vectors, each one of them, the norm is 1, as in this case, so the inner product between a vector and itself will give you 1. And that's exactly what happens here. You see that if I take the same vector and take the inner product, the standard inner product between the two, I'll get 1. But if I take two different vectors, I not equals j, not the same vector, I get 0 because they're orthogonal to each other. And those vectors are the columns of the matrix A. So for two columns Vi and Vj, it stands. Now, when we are looking on A transpose A, what we get is exactly this. So only when I equals j, we will get in this multiplication A transpose A for orthogonal matrix, we'll get 1. But if I does not equal j, we'll get 0. But if we get 1 only when I equals j, so which matrix we will get? We will get the identity matrix. Ones on the diagonal and 0 anywhere else. So this multiplication for orthogonal matrix gives you exactly, because of this, because the orthogonality of the vectors, which are the columns of the matrix, you get exactly the identity matrix. And if you get from this the identity matrix, by definition, A transpose is the inverse of A by definition. And you could look at it as well for A transpose or A transpose A. It will work the same. So it doesn't matter if you take A transpose and multiply by A or A and A transpose. I mean, usually in matrix multiplication, if it's multiplication from the left or the right, it does matter. But here we get the same, from the same calculation, the same idea. Now, orthogonal matrix must be a square. I don't remember this answer. Let's see. Orthogonal matrix must be a square matrix. So This I should have told you that orthogonal matrix must be square matrix, because only for square matrix with the definition that, and I must say that, and it has inverse because the columns are independent, right? I mean, for a matrix with dependent columns, there is no inverse, right? So we need it to be square, so we get an inverse because the columns are orthogonal to each other, so they must be also linearly independent, because two orthogonal vectors are linearly independent by definition. And that is the idea why this holds A transpose equals A minus 1 for orthogonal matrix. Now, the same idea that we talked here and proved here holds for unitary matrix in the complex space, and explains why for unitary matrix B it holds that B minus 1 equals B, I don't know, uh, conjugate B, let's call it like this, right? So the same idea holds for a unitary matrix, as you can see right over here, when the underlying mechanism is the same, and for complex conjugate for unitary matrix, and the proof also rely on Vi times Vj equals 0 and equals 1 only for I equals j, right? Yes. So you can see that the idea is quite the same. The same idea, the same, based on the orthogonality or the orthonormality, if I would say, because the norm of the vectors are 1. And from this, we get that A transpose A equals to the identity matrix, or if you want, B complex conjugate B equals the identity matrix. So we get again that B complex conjugate is the inverse of B in the complex space for unitary matrix, and for real space we are talking about orthogonal matrix, and we get a inverse equals A transpose. So this is the idea that I wanted to show you, why orthogonal matrix stay gives you this very unique, very important, and very useful result. And the same goes for unitary matrix, just in the complex space. So thank you very much. Thanks for Gemini for writing what I needed. And I wish there were no mistakes. And if there were, please let me know. Thank you very much. And this is it.